Hello, students. What we want to do today is to now use the properties, that is the identities of the base A logarithm, to solve more sophisticated equations. We know by definition that we were able to solve many equations just by utilizing the construction between the base A exponential and the base A logarithm, and that was fine. But as we saw with the identities for the logarithm, we had ways to combine multiple log expressions into one logarithm. And so that would open the door to using the toggle, the fundamental relationship between the base A exponential and the base A logarithm, to complete the solution of the equation. So now, again, when you think about expressions you see in science classes or engineering classes where you have multiple log expressions, then we will now have a way to combine them that will allow us to actually have an attempt at solving solutions to equations. So let's go ahead and allow me to share my screen. The very first example should remind you of several of the examples that we did in the last lecture. That is, if I just cover this up, this would just be a problem where we would say, write the two logarithms as one logarithm. And that would be very simple to do. So what you've noticed here, and that what you will see in this section, is you will be asked to solve equations in the real numbers that have forms like this. So what we want to do is to reduce the form of this equation to a very fundamental or simple form for which we can then apply the definition of the base A logarithm. So let's just see how this works. First off, you can see this will be a very simple technique of combining the two logarithms using the product rule. Notice we've got a 1 here and a 1 here, so we can simply write the sum of the logarithms as the log of a product. And notice we have base 3. So equivalently, using the identity, we have the base 3 logarithm of x minus 5 times x plus 3. And this equals 2. So that's the first step, to write two logarithms as a single logarithm. And now what you can see is we can apply the toggle. That is, the power of 3 that equals x minus 5 times x plus 3 is 2. What's a logarithm? Power of the base. So 3 squared equals x minus 5 times x plus 3. Now, of course, this starts to look very familiar that we were doing in the first week of the course. This is simply a quadratic equation, but it's not in a form that would be useful to us because that's not a 0. So now let's go ahead and expand. Let's put all the x's on one side. So we'll have an x times an x squared, and then a 3x minus a 5x, which is a negative 2x. And then, of course, a negative 5 times a 3, which is a negative 15. And then, of course, 3 squared is just 9. And this looks a lot more like what we do when we solve quadratic equations. We've obviously noticed the form, so let's finish it. So now we're just going to subtract the 9 from the negative 15 to give us a negative 24. So x squared minus 2x minus 24 equals 0. Now, at this point, we simply want to use the AC method, and this is very easy. We can just say AC equals, well, 1 times the negative 24. We don't really need the 1 in this case. We'll just simply write this as a negative 6 times a 4. And of course, the negative 6 plus 4 gives us the negative 2. So this factors very easily. So in this case, we have x minus 6 times an x plus a 4 equals 0. Now, of course, this is very useful here. We have 0 product. So we can solve for the values of x that we at least have in the quadratic equation. So by 0 product, we have x equals 6 or x equals negative 4. Now, like I said before, when we deal with exponential equations, they're a lot more resilient as to inputs because the domain of the base A exponential is all reals. We do know, however, that the output of the base A exponential is the positive real numbers, which becomes the domain of the base A logarithm. Basically, what that says, even if the logarithm is shifted or manipulated, that the input of the base A logarithm must be positive. That is, once you compute the value of the argument, it must be a positive number. So when we look here, we can simply check to make sure if we have x equals 6, the x plus 3 is positive, and of course the 6 minus 5 is positive, very simply. But the negative 4 doesn't work here, nor does it work here. So it doesn't matter, just one is enough to throw it out, so we discard this. What we find is that when we use the logarithm identities, we do get something that's true where it's defined, but we see that we have a value of x for which the original equation is not defined. So we discard this. So this will imply that our solution set is just 6. So again, be very careful. It doesn't mean that you have to check everything in the sense that, oh, you've got to go down to the last detail. It's almost like looking for boundary values and checking sign. We simply do enough analysis to make sure that our values of the variable actually preserve the definition of the functions. That's all you have to do. And we have 6 as an answer. Let's try another one. The next equation we have is as follows. I'm choosing these from your homework. These are good examples. So we have the following. We want to solve in R. So here we have the base 10 logarithm of 3x minus 3 minus the base 10 logarithm of 4 equals the base 10 logarithm of x plus 1. Very interesting. So again, the base 10 logarithm of 3x minus 3 minus the base 10 logarithm of 4 equals the base 10 logarithm of x plus 1. Now, like we've had before, notice we have a logarithm here and we have a logarithm here, or 2 logarithms. So we could simply combine them and then do the equality of logarithms by 1-to-1. So that would be a technique. Just remember, however you decide to solve the problem is your choice. If you use good mathematical technique, you will arrive at the same correct solution. So now let's go ahead and combine these. Notice we have the difference of 2 logs, which is the log of a quotient. So we have log of, in this case, 3x minus 3 divided by the log of 4. So we've just got 4 here. So again, the base 10 logarithm of 3x minus 3 minus the base 10 logarithm of 4 is the base 10 logarithm of 3x minus 3 divided by 4. Again, compress into 1 logarithm, equals the base 10 logarithm of x plus 1. So now we'll say use 1-to-1 property. Just like we use 1-to-1 with the base A exponentials. So now if and only if we have 3x minus 3 divided by 4 equals x plus 1. Of course, a very simple equation. We could just now multiply by 4 and collect terms. So we have 3x minus 3 equals 4 times x plus 1, which is just 4x plus 4. And now we want to combine terms. Let me just write these so they're a little bit closer together, and I'll put this side first. 4x plus 4 equals 3x minus 3. And now we'll just simply subtract. We can put everything on one side, but this is a simple equation. So we get an x. And then, of course, subtracting 4 from -3 gives us a -7. Now, this is interesting, and this is what I've said many times. We can write down equations, or we can configure equations that have no solution. Notice the value of x that we get from solving this particular equation gives us a -7. That's the value of the variable. Now, if we go back and check the original equation, we already have an issue here. The -7 renders the x plus 1 less than 0. So this term is not defined. So this is out. So we'll just say, let me write this out. Original equation undefined. Undefined. So no solution. So again, we don't want to assume anything about logarithmic equations. When it comes to a logarithm, we want to make sure that whatever values we get of the independent variable actually work in the original equation. Now, in the previous example, one of the values did not work, but we did get one that was successful. So there was a solution other than the empty set. I mean, when we say there's no solution, that is a solution. I mean, we've determined that there are no values that are real that work in this equation. So again, the value of utilizing the logarithmic identities is that it opens the door to providing a solution. And when we see here, there are no values or no real numbers for which this equation has a solution. So this is very useful to us. Okay. Now the next example, it doesn't matter what I want to be able to do here is use as many of the properties that will build some confidence, because these are not simple equations the first time you do them. So let's try another one that's like the last one, but has just a little bit different twist to it. We have the base 10 logarithm of x plus 4 equals the base 10 logarithm of 5x plus 1 plus the base 10 logarithm of 2. Now, it doesn't matter what the arguments are. You can actually pen your own equations and practice solving them. You don't have to wait on the book. You don't have to wait on me. Once you develop a strategy for solving these types of equations, you can pen your own equations. So now when we look at this, we're thinking, we could do this the same way we did the last one. You're thinking, and that's important. You could also say, well, I could, subtract one of these logarithms and use the quotient rule. I mean, there are many ways that you can do examples. So I don't want you to think that you have to do anything a specific way. But what I like is getting you practice with the one-to-one. So what we can do is combine these two and use the same technique as the last problem. So we have the base 10 logarithm of x plus 4 equals, now we have the sum of logs, which will now be the log of a product. So we have the base 10 logarithm of 5x plus 1 times 2. So this is the base 10 logarithm of x plus 4 equals, I'm going to go ahead and reduce this, just change up the technique just a little bit, just to make it interesting. So we're going to have what, in this case, 2 times 5x, that's a 10x plus a 2. Okay, so that I didn't have to do that simplification here. I could go on ahead and use one-to-one property, but go ahead and do the simplification and then move to the one-to-one. Now use one-to-one property of the base A logarithm. And in this case, the base is 10. So now we can set, again, the arguments equal. So we have x plus 4 equals 10x plus 2. So now we can transpose. So we'll have x from 10x will give us a 9x. And of course, 2 from 4 is just a 2. Well, this is simple. So we just have x is equal to 2 divided by 9. So the value of the variable here is 2/9. Now again, just like with the last one, this is fixed, but of course, 5x plus 1 when x is 2/9 is clearly positive. And of course, 2/9 plus 4 is clearly positive. So this is a check in the sense that we do not have to discard this value. So now we have a solution set of 2/9. Again, when we compare this to the last problem, I want you to see the difference. We use the same technique, but the value for the independent variable did not render a defined equation. That is, this is not a solution of the original equation. When we think about the intermediate equations, for instance, when we think about just starting here and moving forward, that's where we get into a realm, oh yes, we have a solution to this equation. But we have to remember, just like in doing domains of compositions, if we're combining the two functions in composition, then we have to remember the domain of the inner function. It really just depends on where the problem originates. So if we're solving this equation and the intermediate equation is this, then we need to make sure that if we do have a solution to this, that it indeed solves the original equation. That is, the original equation is defined for this value of x, and it is. Think about when you determine domains for logarithms. Instead of trying to do that for an equation, you simply solve the equation and then check the values. That would tend to be a quicker way to do it. Now, of course, you can combine everything and then do the domain calculation, but that would tend to be a little bit longer than just checking the values. So again, your choice in technique, but I think you'll find that as you generate values of the independent variable, it's a little bit easier to check them, okay? So we're developing some basic techniques that have now transcended the other techniques that we had before, in the sense that we can look at more sophisticated equations. Now, one example that I think you'll find, and this is kind of a blast from the past, I just want to write this down just to remind you where we've been, because even though this is simple, it's very important. So we say solve in R. We just want to do a simple equation just to remind ourselves of some of the exponential techniques. We've been focusing a lot on the logarithms, so I don't want to forget these kinds of equations. Notice here, we're asked to solve this in R, and we have 3 raised to the x plus 1 power equals 7. Now, of course, just like I told you last lecture, in the previous week, we could convert this to what? We could convert this to base 3. So let me just remind you of the technique using the toggle, and then remind you of the technique using the change of base, just to kind of reorient us so that we don't forget these important techniques. So first we'll do method 1. It doesn't hurt to review, and especially when the techniques don't tend to stick very well. So what's a logarithm? Power of the base. The power of 3 that equals 7 is x plus 1. So x plus 1 is a base 3 logarithm of 7. Base 3 logarithm of 7. So the toggle is really the quickest way to do it. And then, of course, x equals the base 3 logarithm of 7 minus 1. Now, of course, again, we're thinking of powers of 3. 3 to the first power is 3, 3 to the second power is 9. So, of course, this logarithm would be between 1 and 2, but more close to 2, since we're dealing with an input or an argument of 7. But again, if your client needed a more sophisticated approximation, you could just change this to maybe base E. So you'd have the natural log of 7 divided by the natural log of 3 minus 1. So this would be, again, either of these would provide solutions. This would provide a solution in a base that may be more amenable to what you had available to you. And let me close the argument of the 3 off. Okay, so this is a very simple equation, but again, I just wanted to remind you of its simplicity, but its importance. So we can now use change of base now that we have it formally written down. Last week, we noted that it was basically just the inverse equations, but let's just do method 2 as a reminder of that. Never hurts to review. So now we'll do change of base. So we have 3 of x plus 1, or 3 to the power of x plus 1, will now equal 3 to the base 3 logarithm of 7. And I don't know why I want to put the 3 in parentheses. I guess maybe that's getting to be a habit. So we have 3 in base 7. Now, of course, this is input equals output. The base 3 exponential and the base 3 logarithm are inverses. So if we input 7, the output is 7. But now the bases are aligned, and so we just use one-to-one property. There's no one way to do any problem in many cases, especially when it comes to solving equations. And then equivalently by one-to-one, we have x plus 1 equals the base 3 logarithm of 7. Which is exactly what we have here. So we get the same solution as we have here. So there's no difference. So now that we formally stated the change of base for the base A exponential, this might have more impact than it did last week. So just remember that there is no one way to solve any equation, and a correct technique is a good technique always. Okay? So let's look at an example that has a little bit more challenge, but not necessarily difficult. When you take the calculus, you will deal with some very interesting equations called or functions called the hyperbolic functions, and they are tied into the natural exponential. And so it will be handy to be able to work with functions that are quadratic in the base E exponential. So to get prepared for that, let's look at the following. We have e to the 2x minus 3e to the x minus 4 equals 0. Quadratic form is our friend. Why? Because we understand the theory of the quadratic equation. We don't have to fear it. I mean, we're glad when we see it because we understand it. Now, notice here, we have a quadratic in e to the x because we have e to the x squared, and then we have a non-squared term and a constant. So just by the pattern, we have quadratic in e to the x. The only thing that would make the problem more complicated is that we would be unable to factor, and we would have to use the quadratic formula, but it would still be accessible to us. So now what we can notice by AC, just let me write this in a more specified form. So we have e to the x quantity squared, there's the squared term, plus -3 times e to the x, and I'll just say plus a -4, just kind of kill it with the notation. So now we see we have quadratic in e to the x, and let me click there we go. I was getting a little fuzzy. I start talking and I don't always check the focus. Forgive me for that. I hope that didn't strain your eyes. It was starting to strain mine, so sorry about that. Now we can see that we have the coefficient of the squared term is 1, we have the coefficient of the non-squared term is -3, and the constant term is -4. So again, this is quadratic in e to the x. Now notice, and this is what's so nice about this, if we do AC, we just have 1 times the -4. where the 1 is really important, but we see that the 1 plus the -4 is -3. So this factors by the AC method, and that's good. So equivalently, we'll go ahead and factor that way. So we have e to the x plus 1 times e to the x minus 4 equals 0. So again, quadratic form is a plus, and it occurs very often in the study of mathematics, and especially STEM mathematics. So we don't have to worry about making exotic substitutions. Even if we had to use the quadratic formula, this is still simpler if we just maintain the variables that we have. And now we can use zero product. So we've got if and only if e to the x equals -1 or e to the x equals 4. Now, of course, e to the x equals -1 is undefined. We know that the output of the natural exponential or any base A exponential is positive. So this is undefined. So in this case, undefined. So that does not give us a value of x that we can use. There are no values that solve this equation. But here we're good. We can just use the toggle. In this case, what's the logarithm? The logarithm is the power of the base. So the power of e that equals 4 is x. So x is a base e logarithm of 4. I know that's saying a lot, but it's the truth. What is a logarithm? Power of the base. So now when you look at this is just basically the inverse rules. But this one's good. For instance, the exponential equations are a lot more resilient, okay, because we don't have to worry so much about arguments and their sign. So this is a much more resilient equation. But notice we only get one solution. So in this case, we just have the natural log of 4, which is better than nothing. But no solution is a solution. They're just no real numbers that make it make sense, so to speak. Okay. Now, there is an interesting problem. Where is it? Oh, yeah. This one reminds me of one we did also earlier, but we didn't quite, I don't think we got to the finish line with it. I may have said something about it, but it deserves another presentation. Say we have the following. We have 2 to the power x plus 2 equals 6 to the power 2x minus 5. Now, notice here, in the past problems, we had maybe just a constant here, and then we just used the inverse rules to change the base. Like we wrote the 7 with the base 3 logarithm and the base 3 exponential. But notice here, we have 2 exponential functions, okay? So you might be thinking we could use a particular base and the power rule, like a base e or a base 10, or we could just use change of base, which is fine. I mean, maybe we want to just change the base 6 to base 2, and then if we wanted, we could change the base 2 to base e. Or you could just say, take natural logs of both sides and use the power rule. You've got many, many ways to do this. So just as a practice with the change of bases, that's actually very important. Let's change the base 6 to base 2. So we'll say if and only if 2 to the x plus 2 equals 2, and now we have the log base 2 of, in this case, 6 to the 2x minus 5. So this means input equals output. So again, when we raise 2 to the base 2 logarithm of 6 to the 2x minus 5, we do get 6 to the 2x minus 5. Input equals output. But now you can use the power rule to bring this power to a coefficient. So we have 2x minus 5 to the base 2 logarithm of 6. So when we do the change of base, you can build in the power rule, but I don't often tell students to do that because it might be a little confusing. So now you could just apply the power rule as a second step. No reason why you should make an error when you could just apply this as an afterthought, so to speak. So this is what we would get. And notice now the bases are aligned. So we use one-to-one, use one-to-one property. That we can't begin to think about how important the fact that these functions are one-to-one gives us, the power that it gives us. So if and only if we have x plus 2 equals, now we just set the powers equal. We have, and if you like, I'll just put the log base 2 of 6 out front times 2x minus 5. So now we just want to isolate the x. So let's get all the x's on one side. It doesn't matter how we do it. So we have x plus 2. Well, let's just go ahead and move the x's over. So here we have a 2 times the base 2 logarithm of 6. So that's a negative 2 base 2 logarithm of 6 times the x. And now we'll just take the 2 over. So this will give us a negative 2. And then we have minus 5 times the base 2 logarithm of 6. Now this is kind of busy, but again, we're just isolating the x. So let me review. We have a 2 times the base 2 logarithm of 6 times x, which we move over. So that gives us the negative sign. And then, of course, over here already, we have negative 5 times the base 2 logarithm of 6, which is this term. And then, of course, we transpose the 2 to give us the negative 2. We just got a bunch of negatives hanging out, which we can absorb. So now we have x equivalently. We have x times 1 minus 2 base 2 logarithm of 6 equals, now if you want, we can just factor the negative. We have 2 plus 5 times the base 2 logarithm of 6. Okay? So now we can solve for x. So x will now be the negative 2 plus 5 base 2 logarithm of 6 divided by 1 minus 2 log base 2 of 6. Now, of course, this is what I was talking about. We can just multiply by negative 1 upstairs and downstairs to get rid of all those negatives. So this just gives us 2 plus 5 base 2 logarithm of 6. And just transpose this, just flip it to base 2 logarithm of 6 minus a 1. So this would give us a base 2 logarithm representation of the solution. Again, the exponential equations are very resilient. We have no problem with this number. It's a good number. Now, one thing you might be thinking about is that since we use this one-to-one property, what if we needed a nice approximation of this? And this goes back to what we've been talking about quite often about change of base. And so, for instance, here, maybe we could change these to all natural base, because like I said before, you could have started by taking the natural base of each side and doing the same isolation process. But I wanted you to get some practice changing the base. So now let's just change to base E. So we have x, so I'll just say change to base E, just as practice. If we do as much practice with changing the base, you actually get better at it. Like I say, the key to refining your techniques is using them. So now we have 2 plus, so we have 5. So now we've got ln of 6 divided by ln. Now, of course, notice here, when we change, we've got the ln of 6, and now we have to have ln of the base 2. So let me just review that. We've got base 2, so we have ln of 6, and then we have ln of the old base, so to speak. So that, again, there's not a whole lot of difference here, so it's kind of subtle. And then downstairs, we'll do the same thing. We have 2 ln of 6 divided by ln of 2 minus a 1. Now, of course, we get a common denominator. So we have what? 2 ln 2 plus 5 ln 6. Of course, this is all divided by ln 2. These will absorb, but let's go ahead and write them so you can see it. Do the same here. So we've got 2 ln 6 minus ln 2, all divided by ln 2. Very simple, just a little bit of busy work, but that's all it is. So now, of course, the log 2's absorb. And we're left with, in this case, x, if and only if, x equals 2 log 2 plus 5 log 6 divided by 2 log 6 minus log 2. So what we have here, if we look at this, these two expressions are equivalent, but they're in different bases. So when you look at this, it's less busy. But when we think about the fact that if we had started by taking natural logarithms, we would get something like this. So one thing you'll notice here, which is very interesting here, let's just do a comparison. I like the elegance of my answer, but notice here, you have log 4, which is basically 2 log 2 if you just use the power rule, and then there's a log 36, which is just 2 log of 6. This is kind of a nicer form to write it, but of course this gives you the same thing as you have here. What I tend to want to do is not to apply the power rule as you actually work through these, just simply change the base of the logarithm. And so notice, and this would be an exercise that you can do. Clearly, to do the alignment of the bases is a little bit more challenging, but it's a good exercise. Now, of course, if you were trying to save a little bit of time and you're thinking, what's the quickest way to get to here? You could just take natural logs of each side and use the power rule, and then you get this directly. Okay, so just remember when it comes to equalities of exponentials, we now have the power to change the base, or we could simply have started by taking natural logarithms of each side. Now, how do I get the equivalent solution to taking natural logarithms? I simply change the base 2 to base e, and this is a good procedure to do. So again, take this problem and practice changing base, practice using the power rule. But again, don't move the powers up unless you want to. I mean, of course, this is the same as log of 4. This is the same as log of 36. Either way is fine. I tend to like the expressions written this way, but we know they're equivalent. So let me just write those down. If you bring the 2 up, we have 2 log of 2 is simply log of 4, because 2 squared is 4, and we have 2 log of 6 is simply log of 36. So what you're going to find with logarithms is that the power rule, the quotient rule, and the product rule will be somewhat of a curse, because as you write expressions, they're not going to always look the same. But then as you adjust them using the identities, you will find that you have an equivalent expression. The same will also be true with the trigonometric functions that I keep talking about, not because I'm trying to change the subject, but when you work with identities, especially with trig functions, it's very similar to the tactics and the strategies that we use with the base A logarithm and the base A exponential. Identities are important. We already know that from working with algebraic functions. But what we want to be able to do here is to apply the identities to solve equations and also to practice with the different techniques. Because unfortunately, as you work through STEM mathematics, you're not always using certain topics over and over. You have to remember them, cement them into your long-term memory, and then relieve or rely upon them. Well, you want to relieve yourself by knowing them, obviously, but you want to be able to rely on them so that you can bring them back out of that memory and apply them to problems that you will see in the calculus. Just remember, you don't use every topic every day. There'll be a time when you've got to pull in logarithms, or you've got to pull in theory of equations, or some important geometry. You really never know. So that's why we want to have you as prepared as possible when you take the calculus. So that's all I have to say about this topic today. I hope that you spend plenty of time solving equations and build your confidence so that you feel very secure about this topic. We'll talk to you later.